No, it's fine with me.
And I need to confirm that it will be okay if we record the session.
It's okay with me.
All right, fantastic. All right, so Francisco Cribari is Professor of Statistics at the Federal University of Pernambuco, Brazil. We are honored to have him in this time. I mean, he is a well-respected and highly celebrated researcher. He is actually the former president of the Brazilian Econometric Society and the former applications editor of the Brazilian Journal of Probability and Statistics. We are humbled to have you here with us, Professor. We can discuss at the end of the presentation, the Q&A, and we can translate, no problem. There are plenty of people who can follow the presentation in English as well. If there are problems in translation, we can serve as a translator. Professor Francisco Cribari will give us a talk titled Statistical Econometric Modeling of Double-Bounded Random Variables. Please, let's welcome Professor Cribari. Thank you very much.
Thank you for the kind words, and thank you for the invitation. My topic is Statistical and Econometric Modeling of Double-Bounded Random Variables. And my slides are a little bit ambitious. I'm not sure whether I'll be able to cover everything. If not, I'll just jump over a few slides. But my basic outline is to talk about univariate modeling, linear regression, and time series modeling. Let's see if we can cover all of that. I'm going to start with univariate modeling. And my main topic of interest in the last several years are double-bounded random variables. And what's a double-bounded random variable? It's a random variable that assumes values in an open interval, say from A to B. The most important case is the standard unity interval, where the variable of interest assumes values between 0 and 1, such as rates, proportions, income concentration indices, and so on. And I'm going to focus on the case in which the variable of interest assumes values between 0 and 1. Yeah? There is somewhat related literature that deals with data inflation. It's when the variable of interest assumes values between 0 and 1, open interval, but it may include a few zeros and or a few ones. So you need a model that combines a continuous and a discrete component, and we call those models inflated models, but I'm going to focus on the case in which the variable that we want to study assumes values between 0 and 1, such as unemployment rate and proportions and so on. No? The most commonly used distribution with such data is the beta distribution. No? The beta density is usually written as in this slide, and P and Q are positive valued parameters, and gamma is, of course, the gamma function, and so on. And the mean of y equals P over P plus Q. And the variance of y is also a function of P and Q. And we want to develop regression models based on the beta distribution. So we need to change the beta parameterization a little bit so that one of the parameters is the distribution mean. So that's what I did in a paper with Silvia Ferrari from the University of São Paulo in 2004. We wrote the beta density as a function of mu, where mu is the mean of y, the variable of interest, and phi, where phi is a precision parameter. And why do we say that phi is a precision parameter? Because for a given mean, the variance of y decreases as phi increases. So think of phi as, say, the inverse of a dispersion parameter. We call it a precision parameter. So the higher the value of phi, the smaller the variance of y. And the beta density, the beta distribution is very flexible. In particular, the beta density can assume many different shapes. It can be uniform. The uniform distribution is a particular case of the beta distribution. It can be skewed to the right, skewed to the left. It may have a J shape, an inverted J shape, an U shape. It cannot be bimodal, but except for that, it can assume many different shapes. So it's very flexible for data analysis. And so the beta distribution is commonly used for univariate modeling, but I'm more interested in regression analysis. So in regression analysis, we are interested in modeling the behavior of a given variable, say y, that's our dependent variable, our response variable. And the mean of y is impacted by other variables, which we call covariate regressors, explanatory variables, independent variables. And we denote as x2, x3, yada, 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 up to xp. And we have observations on y, which is the variable that we are really interested in, and the covariates. And we have n, lowercase n, observations on each variable. And what we want to do is to measure the impact of each regressor on the mean of y. And we can do that using, say, the linear regression model, which is a workhorse of statistical modeling. And but there are some problems with that. In the linear regression model, the impact of each regressor is just a constant, which is the regression coefficient associated with the independent variable. For instance, beta 3 is the change in the mean of y as x3 increases by 1 unit and all other regressors stay constant. And we are not going to have such a simple interpretation in more elaborate models, like the beta regression model that I'm going to present. But the linear regression model is not useful for dealing with double bounded random variables, no? Because it may yield fitted values outside the standard unit interval. You may get a predicted unemployment rate which is negative, which makes no sense. So people use to transform, modify the dependent variable so that it assumes values in the real line between minus infinity and plus infinity, and then use the transformed response in the regression analysis. But that's also has some problems because the regression coefficients now need to be interpreted as a function of the mean of the modified response and not as the mean of the response itself. So suppose that y is unemployment rate, I have to interpret beta 2, beta 3, beta 4, and so on as a function of the mean of log of y divided by 1 minus y, which is not sensible. So that's how beta regression came about. It was considered in a few different instances prior to my paper with Silvia Ferrari, but our paper, I think, was the first paper that gave a comprehensive treatment for the model. And we used the beta parameterization that we proposed. And here, y follows a beta distribution with mean mu t and precision phi t. We initially considered phi to be constant, and that was later generalized by Simmons et al. And that's the model that I'm going to present. So the mean of y, that's our variable of interest, is a function of regressors, and the precision is also impacted by regressors. the regressors in the two submodels, they may coincide totally, partially, or not at all. No problem there. And G1 and G2 are link functions. We need those link functions because the right-hand sides assume values in the real line between minus infinity and plus infinity. And mu assumes values between 0 and 1, and phi cannot be negative, so we need those functions. And you need to, in practice, you need to choose which G functions you are going to use. For the mean submodel, the most commonly used ones are the logit function, which is by far the most commonly used, the probit, complementary log, and the Cauchy link function. The logit link function is the one that's most commonly used. For the precision submodel, we can use the log link function or the square root link function. The log link function is more commonly used than the square root link function. So you need to choose those functions when you perform data modeling. And parameter estimation is basically carried out by maximum likelihood. And the betas now can be interpreted in terms of the mean of y and not in terms of the mean of a transformed y, which is nice. The model accommodates distribution asymmetries. As we have seen, the beta distribution can be skewed to the right, skewed to the left, no problem there. Rates and proportions are usually skewed distributed. And also the model is naturally heteroscedastic. And it's heteroscedastic in a way that's very peculiar to rates and proportions. The variance tends to be quite small as mu, the mean of y, approaches 0, 1, and it's larger in the middle region of the distribution support. And the model will never yield fitted values outside the 0, 1 interval, so you are never going to get a negative predicted unemployment rate, for instance. And it's implemented in the beta reg R package. There is this paper that I did with Akin Leis, and it was published in the Journal of Statistical Software that describes how to use the beta reg package and so on. And whenever we fit a regression model, we want to have an idea of the goodness of fit of the model. So in linear regression, we usually compute the I-squared, the coefficient of determination. Here, we can compute two different pseudo I-squareds. They are called pseudo I-squareds because they are not exactly I-squareds. They are similar to I-squareds. The first one I propose in my paper at Silvia Ferrari is just the square of the correlation coefficient between the Y transformed and the fitted linear predictor for the mean submodel. And the second one is the Nagelkerk pseudo I-squared, which also uses information from the precision submodel. You can compute either one. And residuals for such models, in my paper with Silvia, we propose a very basic residual. But after that, in two other papers with Silvia and Patricia Espinheira, one in Journal of Applied Statistics and the other one more recent in Biomedical Journal, we propose different residuals for the beta regression models. In the second paper, we consider a nonlinear formulation of the model. We also developed a local influence for detecting outliers. Model selection for the model was developed in two papers, basically, that I did with Fabio Bayer, which was a former PhD student of mine. He's now professor in the south of Brazil. And one was published in Test and the other one in Communications. And in the first one, we proposed an interesting criterion for selecting the true model using data resampling, bootstrap. And I'm going to try to show, since there are several students, I believe, watching this talk, that it's very easy to estimate those models. So I'm going to use a very standard data set, which is the gasoline yield data. And here, the variable of interest is the proportion of crude oil, petroleum, that we can successfully convert into gasoline and after distillation. And there are some independent variable, mostly the most important one probably is temperature, and also the different type of oils that we are considering. And the sample size is fairly small, which is quite challenging. And we, in my paper with Sylvia, we estimated a fixed precision model. So there are only regressors in the mean submodel, and we consider the logit link. And basically what you have to do, such data is available in the beta-reg package. You just call the beta-reg package, you load the data, and then you call the beta-reg function, and it estimates the model for you. The default link function is the logit link function. And here I'm using batch, which is a series of dummy variables for the different type of oils and temperature. And then it the package estimates the model and gives you the estimates, standard error, z-test statistics, p-values, and so on. So we see that the coefficient of temperature is positive, which means that the higher the temperature, the higher the mean response. The phi estimate here is quite large, it's 440, and it took 54 iterations to converge. The package is quite smart. It starts with a BFGS quasi-Newton optimization algorithm, and then when it gets close to the maximum, it hands over estimation to Fisher's score algorithm. And then, so this is the bread and butter beta regression model. We, in a recent paper with Christine Rauber, who was a master's student of mine, she's now doing her PhD in statistics at Lancaster University in England, and Fabio Bayer. We developed an extension of the model, which was based on a previous paper by Fabio Bayer and Canterli. And the basic idea that we explored was to not estimating, not choosing the mean link function, logit, probit, log, and so on, but estimating that function. So we have a parametric link function for the mean submodel, which is the most important one. And we use the asymmetric rand or das link function. And then we have one extra parameter to estimate, which is lambda. But by doing so, we estimate the relationship between the mean response and the linear predictor instead of imposing a function there, such as the logit link function. And interestingly, the logit link function, which is the solid line here, is a particular case of that family of link functions. And our family of link functions reduces to the logit link function when lambda equals 1. And the C log, the complementary log link function, is also sort of a particular case when lambda converges to 0. But for larger values of lambda, we have more asymmetry. Let me show you how this applies to our gasoline yield data. And I'm going to use the same data as in the previous example. And here, our estimate of lambda, if you look at the caption of the table, is 6.6, which means that we are very far away from the logit link, which would be lambda close to 1. And the gasoline yield regression coefficient now becomes 0.018, which is considerably larger than what we had before, 2/3 larger. So according to this, the second model, temperature has a stronger impact on the distillation of gasoline. And we have also a much higher precision. Instead of 440, we have 942. And then which of the two models is preferable? Let's take a look here. I'm gonna look at the AIC, the BIC, which I call SIC, which is Schwartz Information Criteria, and our two pseudo I-squares. You see that the AIC and the BIC favor the parametric link model. There is a tie in the first pseudo I-square, and there is a slight advantage for our model in Nagelkerke's pseudo I-square. We also use the test of correct model specification, the null hypothesis that the model is correctly specified, and the null hypothesis rejected for the logit link function. You see that the p-value is very small, and the p-value is very large for our model, which means that according to this test, our model is correctly specified. Yeah? So we gained a lot by using a parametric link function, and we have several other results in the paper that I won't have time to show. And you'll notice that the sample size was very small. I just published a paper in PLOS ONE with a PhD student of mine, Ana Guedes, and a colleague of mine, Patricia Espinheira, where we developed Bartlett corrections for the beta regression model. And we get very, very accurate inferences when the sample size is small. I won't have time to go over that paper, but let me just show you one table. You see here that the sample size are 15, 20, 30, and 40 observations. Let's take 20 and nominal level 5%. The standard likelihood ratio test, which is omega, the first line here below the sample sizes. Its no rejection rate, its size is 17.6%, which is over 3 times larger than the nominal level of the test, which is 5%. The next rejection rate is 4.9, and that's from our Bartlett corrected tests. So you see that even with several regressors and very small sample size, we get very accurate inference. And the other two ones are 9.3 and 11.1 are from an alternative finite sample correction developed by Silvia Ferrari and Pinheira, which doesn't perform as well as our Bartlett correction. And there are several applications in the literature, a huge number of applications that use beta regressions. I'm going to just mention a few. I did the 2 applications, the 2 papers, 2 applied papers that were published in Intelligence, which is a journal by Elsevier, where we model the relationship between average intelligence and the prevalence of religious disbelievers. And in the first one, we collected data for several countries in the world. And in the second one, we focused on the United States. And then we were able, in the second one, we also used quantile regression, and we were able to uncover some interesting results that were not available in the literature. And there is also another paper in Intelligence that I did with Tatiana Souza, which is a former PhD student of mine, where we explore and model the relationship between homosexuality, non-acceptance, and intelligence and religiosity as well. We gathered data from 52 countries, and it was also published in Intelligence. There is a recent paper by one of my colleagues, Gauss Cordeiro, and co-authors, and they modeled COVID-19 mortality rates in Europe using the beta regression model. There is also very interesting paper in PLOS ONE that was recently published where they used county level data for the United States to model COVID-19 fatality rates, and they use as regressors alcohol consumption and some interesting covariates. So beta regression model is very commonly used in applied literature, in finance, in hydrology, economics, engineering, and so on. And I don't have enough time to go over all the things that I have been doing with the beta regression model, but I just wanted to give the students an overview of some of the things that I have been working on. And my other line of research regarding modeling of double-bounded random variables deals with time series modeling. Here, the interest lies in observing the behavior of a given variable over time and possibly producing forecasts of future values. And time series data, we know, this typically displays zero correlation. The value of our time series today is not independent of its value yesterday and so on. And we have to take that into account when we model the data. And then we could use standard tools like the Arma model, exponential smoothing algorithms, and so on. But a former student of mine, Andrea Rocha, who is now teaching at Saudi Arabia, we proposed a model that's called the beta Arma model, which is a time series model for double bounded random variables, which is somewhat similar to the standard Arma models, but there are some differences. So suppose that we observe the behavior of y, the variable of interest over time, and we are going to do everything conditional on an information set, which is calligraphic f subscript t-1. So at time t, we know a lot of information on things that happened before that time. And so we're going to condition on that because that's known information. And we are going to use the same parameterization used in the beta regression model. So phi, again, is a precision parameter. Here we consider the case that the phi is a fixed constant and the mean of y evolves over time. And that's the model that we propose. So G is one of those link functions, logit link and so on. Mu is the mean of y at time t, mu t. Alpha is a constant, and then we can have regressors in the model as long as they are not random. For instance, we may include regressors to account for a time trend or for seasonal fluctuations. And then we have some autoregressive components and some moving average components as well in the model. And G is a link function, and P and Q, just as in the standard Arma model, are the dimensions of the autoregressive and moving average polynomials. But this model, it looks like to be very similar to the Arma model, but somewhat different. This model is observation-driven, and the Arma model is innovation-driven. And that's a difference that most people don't appreciate. That's why I'm trying now to make it explicit, because I noticed that some people who were writing papers on beta Arma models didn't realize that. If you take a look at the equation of the model, just look at the last term on the right-hand side, the summation over J going from 1 to Q. You'll notice that there are past errors there. RT minus 1, RT minus 2, RT minus 3, and so on. But now I'm gonna say something that's extremely important, and it's gonna take about 4 seconds. The current error term, RT, is not in the model. end of the 4 seconds. And that makes this model very different from the standard Arma model. So this model is observation-driven. It's not innovation-driven because the current error term is not in the model. The standard Gaussian Arma model is innovation-driven. What does that mean? Let's take a look at that. Let me try to be very clear here about that. So I'm going to take the simplest Gaussian Arma model, which is the AR1 model. And YT, which is the value of the process today, is equals, my notation here is very bad because I'm using phi, but phi I'm using to denote another things, but let's go on. A parameter, an autoregressive parameter times the lagged value of the process plus RT. This RT is the current error term. There is no RT in the beta regression model, okay? So how does this process evolves? First, RT assumes a value. We get a realization, say, from the normal distribution. We get a number for RT, 1.47 or 3.26 or minus 1.82 and so on. And then we add that to phi times YT minus 1 to get the value of YT. So the process evolves through a sequence of white noise innovations. And that does not happen in the beta Arma model. In the beta Arma model, YT is a realization directly from the beta distribution, conditional on previous information. And so that's fairly different from the Gaussian Arma model. And now we define, and define is an important word here, we define the way that we want the error to be. We can use the error in the predictor scale or error in the original scale. It doesn't make a difference because RT is not in our model, only past values of our RT. And we estimate the model using conditional maximum likelihood. And this model was extended to account for seasonality in a paper that I did with Fabio and Renato Sintra, a colleague of mine, in the Journal of Statistical Computation Simulation. So we have a seasonal formulation of the beta Arma model. There is also an extension of the beta Arma model that accounts for fractional integration. I did not write the paper. The paper was written by Guilherme Pumi and Fabio, Tayane Praz, and co-authors that was published in the Journal of Statistical Planning and Inference. And I did a recent paper on that. Let me just briefly mention. It was a paper that was published in Envirometrics with Guilherme Pumi, Fabio Bayer, and a PhD student of mine, Vinicius Scher. And we developed goodness of fit tests for beta Arma models, and we applied that to hydrology. And the null hypothesis that the model is correctly specified, and the alternative hypothesis that model specification is in error. And we test the null hypothesis that the first M residual autocorrelations are jointly equal to 0. We can use the standard tests that are already available in the literature for Gaussian Arma models, such as the Lungi-Box test and Monti's test and so on. But we proposed a new test statistic, which is this one. I don't have time to go over all the details there, but instead of using residual autocorrelations, though the pi hat here is the case partial residual autocorrelation. And then we use a transformation on that. And then we prove our main result is this, is that we have a set of assumptions that as long as they are okay, as long as they hold, the null distribution of our test statistics converge to a chi-square test statistic so that you can use asymptotic critical values obtained from the chi-square distribution. We proved that result in the paper. And as a corollary, we show that most standard test statistics that are available for Gaussian Arma models are also asymptotically chi-square distributed under beta Arma dynamics when the null hypothesis is true. That's a corollary of our main result. And then we show a lot, many Monte Carlo results. And we also present an empirical application. And overall, the Monte Carlo results favor our tests. This is just one of the results. Those are two power curves. So those are non-null rejection rates. You see that the curve with the dashed curve in both plots, that's for 50 and 250 observations, respectively. Those dashed curves correspond to our test. So our test is considerably more powerful than other tests, especially in cases like this one that you neglect to include in your model, fail to include in the model moving average terms. And my current research with beta Arma models, I'm coming to the end of my talk. My current research deals with beta Arma model selection. And we have a set of candidate models, and we want to select the best fitting model for out-of-sample forecasting. So we need to penalize the augmentation of the model dimension. And we consider standard criteria that are available in the literature. We have a lot of more results in the paper. We also consider model selection based on forecasting accuracy and things that I don't have time to go over. And we consider many different criteria. I'm going to just mention a couple of them, which is the AIC, Akaiki's information criterion, which is well known. And the Schwartz information criterion, which is most people call the Bayesian information criterion. We use those two criterion, and also Hennig-Quinn, AICC, and several other criteria, WIC, and so on. But we propose using a data resampling criterion based on bootstrapping. And we use something that's very similar to a proposal that was made in another kind of literature on state space models. And the idea here is to create pseudo time series, fit the model for those pseudo time series, and then use that information to estimate the penalization term B. So that's why we have a B hat over there. And then we create capital N artificial time series. And then we estimate capital N, we estimate the model capital N times. And then we compute this criterion here. I don't have time to go over the details, but this thing performs quite well in finite samples. Huh? We have a lot of Monte Carlo results in the paper. And they all show that this bootstrap criterion outperforms considerably AIC, BIC, and so on, especially when the sample size is small. We did a lot of simulations using parallel computing in R. We do 5,000 Monte Carlo replications and 500 bootstrap replications. Bear in mind that for each model, we have to estimate a bunch of models in order to select the best performing model. So the simulations are very computer intensive. We carried out them at the Supercomputing Center at Federal University of Rio Grande do Sul in Brazil. And so this is just a sample of our results. Here, the sample size is very small, just 50 observations. And we are reporting the proportion of correct model specification. And then you see that the AE empirical information criterion that uses bootstrap performs a lot better than AIC and SIC. For instance, when the true data generating process is beta autoregressive 6, we with only 50 observations, we identified the correct model nearly 66% of the time, and the BIC only 13% of the time. And if we increase the sample size to 250, and the true underlying process is autoregressive, they all perform well. But with moving average processes, and especially mixed process with autoregressive and moving average terms, we get considerably better results. For instance, with moving average models here, you see that with beta MA6, we are getting it right over 60% of the time, and AIC is getting it right less than 20% of the time. Here are some results for models that have autoregressive and moving average terms. You see that our bootstrap criterion outperforms the BIC and AIC considerably. We have many more results in the paper. I don't have time to show them, but we try to produce a table that summarizes all results. So we average all results by sample size, and we have a global figure as well. Let's look at the global figure. For all simulations, we get it right 83% of the time, and the other criteria considerably less than that. Especially when the sample size is very small, we do very well. And then we use that to forecast the proportion of stored energy in the south of Brazil, in hydroelectric power plants there. There are basically two types of reservoirs. There is the line reservoir, that's the main one where the water drops and energy is generated, and there is an accumulation reservoir where water sits still and it's only used whenever necessary, and we want to predict the use of that. In the south of Brazil, we collected data from ONS, which is the main agency in Brazil. We have 214 data points. We removed the final 6 for forecasting accuracy evaluation. So our time series has 208 observations. We also consider subsamples, sorry, of 75 and 150 observations. This is our time series, and the correlogram and the partial correlogram of the series. And then we also used Arma models and exponential smoothing, and we show that in some cases, they yield improper forecasts. They forecast more than 100% of utilization of the reservoir, which makes no sense. And then we select the best model, and then we do out-of-sample forecasting. We also do portmanteau testing to check whether the models are correctly specified. And overall, I'm going to go fast here. Overall, the models that are selected using our bootstrap criterion perform a lot better than the models that are selected using AIC, BIC, WAIC, AICC, BICC, and so on. In all sample sizes, 75 observations, 150 in 2008. They select different models. So for the first 2 sample sizes, our bootstrap criterion selects the beta AR3 model, and for the full sample size, the beta Arma SU3 model. And then we evaluate forecasting accuracy using the mean absolute prediction error. And we have a lot of results, but here is a sample of results. You see that the numbers in boldface are the best results. And in all but one case, which is the second sample size, and age equals 5. Age is the number of steps ahead that we are predicting. The models that are selected using our bootstrap criterion perform better than models that are selected using other criteria. No? So we do a lot better. I don't have time to go over that in all cases. And we also investigate the impact of outliers on model selection. We artificially introduced outliers in the real data by multiplying certain observations by numbers that are less than 1 or more than 1. And we introduce an outlier at 25% of the series, the middle of the series, 75% of the series, and then 3 outliers at the same time. And we find that model selection is not impacted by that. So the criteria, the different criteria keep selecting the same model, even though the data now have outliers. But parameter estimates are obtained using maximum likelihood. They are somewhat impacted by the outliers. No? But interestingly, the short-term forecasts, especially the next 2 forecasts, if you are forecasting next month and the month after that, those forecasts are not very impacted. Those forecasts are very impacted by the outliers, and forecasts for horizons equal 3 or more are not very impacted. So we plan to study that in more detail in future research. And this particular paper here on beta Arma model selection is accepted for publication at the International Journal Forecasting, and it will probably come out next year in 2022. It was accepted, I believe, a month ago or so. So to finalize, I don't want to go over my time limit. My main interest here was to show you different approaches to model double-bounded random variables that assume values between A and B. It could be -10 and 10, 0 and 100, but the most important case is between 0 and 1, such as rates and proportions and income concentration indices. I try to show univariate modeling very briefly, beta regression and time series modeling. The beta regression model has been extremely used in the literature in applied fields over the past several years. And the beta Arma model, it's starting to be quite used. There is a recent paper on using Bayesian models with the beta Arma, but I believe they only consider autoregressive terms. There is a recent paper in International Journal Forecasting that uses the beta Arma model to predict the proportion of work-related accidents in some activities and so on. And the main references are the paper by Akaeke, the Aranda Ordaz paper in Biometric for the parametric link function, my paper with Silvia Ferrari on beta regressions, Nigel Kirk on pseudo I-square, my paper with Christine, my former student who is now at Lancaster University. It was published recently at the ASTA, which is the journal of the German Statistical Society, in my paper on beta autoregressive models with Andrea Rocha. My paper with Vinicius Scher, which is my student in the biometrics. So those are some of the main reference. And that's it, folks. And I am open to comments, suggestions, and even threats.
Thank you so much, Professor Cribari. And you were right on time. I was about to open my mic and I was hesitant to tell you, are you close to wrap up? So thank you so much. Para la audiencia, si tienen alguna pregunta, algún comentario, o como dice el profesor, alguna amenaza, él está más que abierto a hacerlo. Sea en español, en portugués o en inglés, podemos colaborar. No sé si alguien quiere abrir su micrófono o levantar la mano, con gusto le damos la oportunidad.
Bueno,
Por favor.
Francisco?
Sim?
Márcia.
Oi,
A minha
Márcia.
pergunta vai ser em português. Na verdade, é só uma curiosidade. Primeiro, parabéns pela ótima apresentação do seu trabalho.
Obrigado.
Uma curiosidade sobre o modelo beta. Tudo que vocês desenvolveram uma grande teoria em termos da distribuição beta, mas eu fico curiosa em saber se vocês têm alguma versão multivariada. Ou seja, se é possível pensar não só no vetor de distribuições que tenha truncamento nesse vetor. Se tem alguma ideia nesse sentido, e queria que você comentasse um pouco sobre isso.
Se você... Vamos pensar no termo multivariado. Se você tem... Eu estou entendendo que a sua pergunta é para o caso onde Y é uma matriz e não um vetor, né? Se Y for uma matriz e não um vetor, aí depende se os componentes de Y somam 1 ou não. Por exemplo, imagine que é proporção da renda gasta com alimentação, proporção da renda gasta com diversão, proporção da renda gasta com transporte e proporção da renda gasta com outros itens. Então, essas 4 proporções somam 1. Né? Então, para esse caso, existe um modelo de regressão de Dirichlet. Inclusive, tem um pacote no R para regressão de Dirichlet, tem papers sobre isso. Eu acho que um colega meu, Klaus Vasconcelos, fez coisas nessa linha. Então, se as suas proporções somam 1, tem um modelo de Dirichlet. Se são proporções não relacionadas, que não necessariamente somam 1, eu não tenho acompanhado a literatura sobre isso, não. Então, se forem proporções, proporção da renda gasta com alimentação, proporção de alunos que não completam a universidade, se forem proporções que não somam 1, eu não conheço assim de cabeça, provavelmente já tem alguma coisa. O caso mais interessante é o caso onde não tem muita coisa, que é o caso de dados que os estatísticos chamam de longitudinais e os economistas gostam de chamar de dados de painel, né? Que é um caso muito interessante, porque você segue algumas unidades ao longo de alguns períodos de tempo. Tem uma tese de doutorado na USP, que eu não me lembro mais de quem é, eu acho que foi orientada pela professora Viviana Giampaoli, onde eles trabalharam com o caso de dados longitudinais com regressão beta. Depois, alguns anos depois, eu procurei algum artigo publicado, não encontrei, talvez não tenha procurado bem, mas esse é um caso que vale a pena desenvolver, porque tem muitas aplicações com dados longitudinais e tem pouca coisa feita em regressão beta com dados longitudinais. Eu esqueci de mencionar, não tive tempo, que também tem uma certa literatura, tanto em regressão beta quanto em modelos dinâmicos, com inferência bayesiana. Em modelos dinâmicos, a Cibele, da UNB, e o Hélio Migon tem 1 ou 2 papers com modelos dinâmicos de séries temporais beta. Um deles, eu lembro, publicado no Computational Statistics and Data Analysis. E a parte bayesiana, o primeiro artigo que eu me lembro, depois da publicação do meu artigo com a Silvia, foi um artigo no Australian and New Zealand Journal of Statistics, que na época eu achei muito interessante, porque era muito voltado para aplicações, fazendo coisas parecidas com o que a gente fazia com inferência bayesiana. Então, respondendo a Márcia, eu botei aí a parte bayesiana aí de
Não,
brinde.
A minha pergunta era justamente aquela ideia, aquele segundo exemplo que você deu do vetor onde não soma 1, né?
Não, isso aí
era um pouco nessa ideia que eu pensava assim, se você pensar numa distribuição multivariada no contínuo e fizer truncamentos, né? Talvez seja uma ideia de restringir, né, esses espaços. Isso é só um pensamento um pouco...
Você pode procurar. Eu me lembro que eu cheguei a ver alguma coisa, mas eu não me lembro exatamente o quê. Mas você vai ter que ter uma distribuição muito variada, você vai ter que observar as distribuições marginais e assim por diante. Né?
Não, tudo bem.
Mas tem coisa interessante para fazer aí, se você quiser trabalhar nisso. Eu acho que você vai ter muito material para trabalhar. Obrigado pela pergunta, Márcia.
Bien, gracias. ¿Tenemos alguna otra pregunta?
Oi, professor Francisco. Carolina Marchán, por aqui.
Ô, Carolina, tudo bem?
Tudo. Não, só felicitar você por sua palestra, seu trabalho, o trabalho que você fez nessas duas linhas de pesquisa, não? Parabéns. E um prazer vê-lo e ouvi-lo.
Muito obrigado. A Carolina é uma grande pesquisadora e um dos pontos altos do meu currículo vitae é um dia ter sido professor dela.
Não, um prazer para mim tê-lo como professor.
Excelente. ¿Algún otro comentario, otra pregunta?
Harvey,
Sí, por favor.
gostaria de fazer uma consulta ao professor Francisco com relação a se existe alguma forma de transformar os dados que têm suporte nos reais positivos para poder usar uma regressão beta, por exemplo, deixar no intervalo 0,1. É só uma curiosidade.
É mais difícil você fazer essa transformação, mas esse tipo de transformação é muito problemático porque eu não gosto de transformar dados, porque se você pega um seu Y e faz algum tipo de transformação no seu Y, estima uma regressão, os coeficientes de regressão serão interpretáveis em função da média do Y transformado. Então, imagine que o meu Y... Vou fazer o caso de proporção. Suponha que meu Y é proporção da renda gasta com alimentação. Então, esse é meu Y. Então, eu faço log de Y dividido por 1 menos Y e faço uma regressão linear. Os meus beta 2, beta 3, beta 4 vão ser interpretáveis em função da média da seguinte variável, log de consumo dividido por 1 menos consumo. E eu não posso colocar esse valor esperado para dentro, porque tem uma coisa que atrapalha muito a vida da gente em probabilidade, chamada desigualdade de Jensen, que é desigualdade de Jensen, como chamam, que diz que se G é uma função não linear, o valor esperado de G de Z é diferente de G de valor esperado de Z. Então, a gente perde a interpretação dos coeficientes, que é mais ou menos o que acontece quando a gente usa transformação de Box e Cox, isso também acontece. Então, se você tem uma variável que assume valores positivos, aí o mais interessante é usar um modelo gama gaussiano inverso ou um modelo que a Carolina, aí, uma grande desenvolvedora, o Victor Leiva, que é o modelo Birbaum-Saunders. Então, tem modelos que são específicos para esse tipo de variável. Né? E tem um modelo também recente do Marcelo Borghignoni e colaboradores, que eu acho que é o modelo Beta Prime, que também eles desenvolveram. Eu acho que o artigo saiu na Netron, eu acho, nos últimos 2 anos. Então, tem vários modelos para esses casos. Mas a regressão beta surgiu porque eu fui co-orientar uma tese de doutorado de economia, onde a aluna queria modelar coeficiente de Gini, que é de concentração de renda. E aí ela estava estimando regressões lineares, que não faz sentido. A gente transformou o coeficiente de Gini e usou numa regressão, mas a gente esbarrou nesse problema da interpretação dos parâmetros. E aí ela defendeu a tese e foi aí que eu fiquei conversando com a Silvia e a gente terminou tentando desenvolver, porque a gente viu que tem muitos modelos para Y entre menos infinito e mais infinito, tem muitos modelos para Y positivo, mas não tem muitos modelos para Y entre 0 e 1, modelos mesmo, desenvolvidos em generalidade ampla, e aí foi que a gente se preocupou com esse caso. Mas obrigado pela pergunta.
Certo. Muito obrigado, professor.
Excelente. ¿Alguna otra pregunta, otra intervención? En ese caso, espero... Javier, no sé si quieres decir algo.
No, nada.
Ya, perfecto.
Yo me estaba preparando para la siguiente, para
Listo.
presentar a la siguiente conferencia.
Listo.
Sí.
En ese caso, quisiera agradecer una vez más a la audiencia y voy a pedirles que esto sale un poco de protocolo, pero si pueden abrir su micrófono y dar un aplauso de gratitud al profesor Cribari, lo agradecería muchísimo.
Oh.
Professor Cribari, we thank you very much for your intervention. It was packed,
Yeah.
truly, but hopefully these kind of interventions give the opportunity to our students, our colleagues, to who knows, inspire themselves to go through these kind of topics, and it's truly inspiring, and we are, as I said, humble and honored to have someone of your stature with us. So truly, thank you so much.
Thank you very, very much.
Muy bien, continuamos entonces y quisiera entonces darle el control a nuestro director de doctorado, el doctor Javier Contreras.
Ok, muchas gracias, Harvey. Profesor Reinaldo, si usted está por ahí, puede proyectar su presentación.